So as no one has joined yet, so I'll start the discussion, and probably you can see this from recording. Okay. So I'll start with a orthogonal basis. Yeah. So previous week I have discussed about last I have discussed about that that projection on a line, right? So today I will start with a orthogonal vector, orthonormal vector, and how to design or basically Gram-Schmidt's process. Okay. So first is orthogonal vector. So we have studied in previous class as well that what is orthogonal vector if qi, so two vectors, let's say qi and qj, so they are said to be orthogonal if q, sorry, so they are said to be orthogonal if qi transpose qj is equals to 0 for I not equals to j. Okay. So this is basically orthogonality. That means two vector when we do the dot product of two vector qi and qj, then we get that this dot product, the resultant uh, the resultant value of this dot product becomes 0. If this comes out as a 0, then it's the orthogonal. And orthonormal is basically similar, just one extra input, one extra condition added to here. Similarly, I'm considering the these two vector qi and qj. So they are said to be orthonormal if one first thing qi transpose qj is equals to 0 if I, sorry, for I not equals to j, and this multiplication gives 1 for I equals to j. Okay, so when we multiply these two vector, if qi transpose qi will give us a 1. Okay, that means the two norm of that vector is basically that no, the length of the vector should be 1. Okay, so when we stack all those orthonormal vector into a matrix, in generally we call it, I mean there is no specific notation for this, but in generally we call that matrix as a q matrix whose all columns are orthonormal. We denote it by q. So if I say that q1, q2, q3 up to let's say qn, so this is basically all QIs, all these QIs where I runs from 1 to n, all these QIs are orthonormal. Then this matrix is called orthonormal matrix, and this is very special matrix because if we work with this matrix, it's very easy. Working with this matrix is basically very easy. Why it is easy? Because the first thing that we know that Q inverse is basically Q transpose. So we know that how much difficult to find out inverse of a matrix, specifically square matrix. So I'm considering here is a square matrix because we do not have any inverse for rectangular matrix. So we know that how much difficult it is to find a inverse of a square matrix, right? Because we need to find out the determinant first, okay, and then we need to find out the cofactor matrix, and then we do this transpose, and then we do the division with this determinant. So there are lots of procedure, right? So with the increase of the number of rows and number of columns, this whole inverse process, the computation of inverse is basically very cumbersome process. But if the matrix is the orthonormal matrix, means whose columns are orthonormal vectors, so then it is very easy to calculate the inverse. Just we need to do the transpose. Okay. So definitely, obviously, then in that case, Q transpose or Q transpose Q is basically we'll get I. Why? How we'll get I? Because if we do, let's say, Q transpose, so that means this is Q1 transpose, this is Q2 transpose, and up to this is Qn transpose, right? And this is multiplied with Q1, Q2, up to Qn, right? So ultimately what we get Q1 transpose Q1, right? Which is 1, then Q1 transpose Q2, which is 0, right? So I'm not writing this 0, and this Q1 transpose Qn, because when I not equals to j, it gives us 0. So similarly 0, this is Q2 transpose Q2, and up to that Qn transpose Qn. So, so obviously for orthonormal matrix, a orthonormal vector, this when I equals to j, that means Q1 transpose Q1 is 1, 0, up to 0. This is 0, 1, 0, and this is 0, 0, 1. So we will get identity matrix. Okay. Now, another orthonormal matrix is basically the example of another orthonormal matrix. Is rotation matrix. So what is rotation matrix? So what is rotation matrix? So rotation matrix, some things look like that. So Q equals to cos theta sine theta minus sine theta cos theta. So these vectors, each vector are orthonormal to each other, because we know that cos square theta plus sine square theta is basically 1, right? So this is known as the rotation matrix. Permutation matrix, another example is this is number 1, this is number 1, number 2, permutation matrix. So what is permutation matrix? We know that permutation matrix are basically, we have already studied permutation matrix, which are identity matrix, but rows are basically jumbled up. Like we are permuting the vectors, right? Something like uh, permutation matrix is something. So identity is also a permutation matrix, but it does not interchange between does not interchange the rows of the vectors, right? But let's say 0 1 0 0 0 1 and 1 0 0, right? So this is one of the permutation matrix. So what it does, it basically, if we multiply xyz with this, so first it will give y z x, right? The resultant vector that we get is basically y z x. So it is basically permute the interchange the rows. Okay. So permutation matrix is also an example of orthonormal matrix, right? Because we know that all the vectors are orthonormal to each other. Another matrix is the reflection matrix. So reflection matrix is basically something like this. Q equals to I minus 2 U transpose. Okay. So where U is any unit vector. So unit vector means u is itself unit vector means the norm of u square is basically 1. That basically does mean of a unit vector. Okay, so if we do the q transpose over here, which is nothing but a q inverse as well, so this is something that we get. So I transpose is I minus 2 u. Since this is a scalar, we do not need to do anything. So u transpose, what we get u 2 u transpose of transpose, that is u and then u transpose. Okay, so what we get q transpose q, what we will get is I minus 2 u transpose into I minus 2 u transpose. So this is simply q, right? So what we get, I multiply I'll get I, because I square is I itself. I multiply this is minus 2 u transpose, this is minus 2 u transpose, and this is 4 u transpose u transpose. So this is what I get, minus 4 u transpose plus. So here if you see u transpose u transpose. So since q is an unit vector, so this term will become 1. So what we'll get, I minus 4 u transpose plus 4 u transpose, so I will get I. Q transpose q is basically comes out as a I. So here q transpose q is also basically q square, because in case of reflection matrix we have seen that q transpose is equals to q, right? So these are all the example of orthonormal matrices where the vector column vector of these matrices are basically orthonormal to each other. Okay. Mm. Now, what do you mean by reflection? So if I'm giving and one example of this reflection matrix, so if I consider u as a unit vector, so this example of reflection matrix. So this is basically an example of reflection matrix. So let's say consider u is basically an unit vector 1 0. Okay. So if you take a norm of this u, we'll get answer is basically 1, right? 1 0. Now what q is said, reflection matrix q is basically I minus 2 u transpose, right? So I is basically, since it's a 2 cross, I mean the matrix in 2 dimensions, so definitely we have to consider 2 cross 2 matrix minus 2. So this is 1 0, and then u transpose, this is 1 0, right? So what we'll get, 1 0 0 1 minus 2, this is 1, this is 0 0 0, right? So what we'll get, it's a minus 1 0 0 1. So if we multiply this and they do the subtraction, we'll get. So why it is called reflection? So it's something, let's say I'm considering v equals to x and y. Okay, now qv is basically minus 1 0 0 1 x and y. So this is what I get, minus x and y, right? So this is basically a reflection of x coordinate across y. So if I consider this is a x coordinate, y coordinate, this is x, y axis, this is x axis. So if the vector v is something like that, which is xy, then its reflection is something with the same y but negative x, which is called v prime minus x and y, right? So this is completely a mirror, a reflection of something. So now comes to the Gram-Schmidt process. So we Gram-Schmidt process, by using Gram-Schmidt process, we basically design an orthonormal vectors. We can design the, sorry, we can design the orthonormal vectors. Even in 3D, or I mean, since we cannot visualize beyond 3D, right? Because our world is basically in 3 dimension. We cannot visualize beyond 3D. So using this Gram-Schmidt process, we can design our own coordinate system. We can basically design our own coordinate system. So let's say we have 3 vectors A, B, C. Okay. So let's say we have 3 vectors A, B, and C. Okay. So now these vectors are, I'm not saying that these vectors are orthogonal, orthonormal. I'm not saying anything of this. But the only thing that is given to you, that we have a 3 vectors and they are independent. Obviously, they are not dependent. So the main thing that is given to you, all these vectors are basically independent. Okay. So now we are basically intent to design an orthonormal vectors. So orthonormal vectors I'm considering, I'm denoting with a capital A, B, and C. So how to design an orthonormal vector? So first, let's say we have a vector something like A. So this is something like A vector, right? I guess something over here. So this is, let's say, A vector. I'm considering as a capital A. Okay. Now we have to choose a vector as a base vector, and using that base vector, we are define our other orthogonal vectors, which are orthogonal to each other basically. So this is basically A vector. Now we have a B vector something. We have something like B vector something like this. Let's say this is something like B vector. Okay. We do not know. I mean, they are definitely, we can see that A, B are not orthogonal to each other. There is some angle between them, and which is not 90-degree, right? Orthogonal means all the vectors should be at 90-degree from each other, right? So we have studied projection, right? So now we are basically try to project this vector onto the A vector. Projection on a line, we have studied projection on a line. So we are basically try to project this vector onto that vector. So we call this is basically the projected vector of B on vector A. So we call it P vector. Okay. Now our result, we need to find out the B vector, that which is orthogonal to A vector. So in this picture, which portion is basically orthogonal? As we see, this one is basically orthogonal to A vector, right? So we need to find out this error. So what is error? We call it B, capital B, because I have said that we call the orthogonal vectors by its capital version. Okay. So capital B is basically nothing but a small b minus p. Just like we have studied previous week how to do the projection of a vector on a line. The same thing. So what we have studied, so if you see, error is basically b minus p, right? It's nothing but a b minus p. And we have studied that this p is something like that. A transpose divided by A transpose A into B, right? So here we are doing something like that. So it's basically B minus A transpose, which I'm calling as a small A transpose B by A transpose. Don't confuse with this capital version of vector by matrix. Normally we denote matrix by a capital letters, but here I'm considering that particular this orthogonal vector I'm considering as the capital of capital letter. So A transpose A into A. So this is how we create a B. So after creating, so this is B. So after creating B, we can shift it over here. So this is basically this vector and this vector are parallel. So we can say this is as a B vector. Okay. Now they are orthogonal. So we have A vector, we have B vector. Now we need to find out a C vector. So we have a C vector, something like we do not know. Maybe a vector is something like this. Let's say this is called C vector. Longer. So let's say I call this vector as a C vector. Okay. So similar thing. So we have to project this C vector on this capital V vector as well as on capital A vector. Okay. Because we need to find a vector which are orthogonal to both. It's not that we have to, it's not that just only projecting this vector on B and we get that thing. No, we have to make sure, since it is difficult to write a 3D picture in a 2D paper. So it's something like we have to project we have to project the C vector on B vector and A vector as well. Okay. And then what we get a capital C vector, which is something like how we'll get this small c minus first error, subtract this error, subtract the error for A vector, because we projected C vector on line A, right? So we need to subtract the error for that. And then we projected C vector on line B as well. So we need to subtract for that. Okay. So now the vector that we got basically is something like, let's say something like that. So this is now my orthonormal vector, which are 90-degree, whose angle are basically 90-degree with each other, right? So is this thing clear to everyone? I hope it is clear to everyone. So it's basically, you can think of like it is basically, you can think of it like we are projecting this vector. We are basically here I have basically projected this vector on AB plane. We have basically projected a vector on a plane. Okay. So means we projected a vector on a plane, means we projected vector individual line on AB plane, because we do not have a equation of plane. We only have a equation of that line. Okay. So we basically projected the C vector individually on B vector and A vector as well. So is this whole thing clear to everyone? I hope it is clear to everyone. So now this is basically your orthogonal. Okay. So since it is orthogonal, so we need orthonormal. So if we divide this vector by its if we divide a vector by its length, we get an orthonormal vector. So let's say we have a vector v. Sorry. So we have a vector v. Okay. So this is not an this is orthonormal means unit length. The length should be unit. This is not an unit length vector. So make a vector unit length. Let's say v prime unit length vector. Let's call it a v prime, which is basically v by norm of v. We have so q1. We can as we have already discussed that we are defining these orthonormal vectors and orthonormal q. So q1 is basically a, which is not a unit length. So we divide it by norm of a, right? We call it q2 is b. We divide it by its norm of b. That is the length of, and q3 is capital C. Obviously, don't confuse with the small c. The norm of c. So now I have an example with the Gram-Schmidt process. So the example says we have an independent non-orthogonal vectors A, B, C, and we need to form this Q1, Q2, Q3. So we have three independent non-orthogonal vectors A, B, and C respectively. What are those vectors? So vector 1 is 1, -1, 0. Okay. Vector B is something like 2, 0, -2. And vector C is something like 3, -3, and 3. Okay. Now find these. Basically, we need to find the orthonormal Q1, Q2, Q3 using a Gram-Schmidt process. So first, what is basically the first thing that we have to do? We consider this capital A as a vector. Okay. So we need to do it a base vector. Okay, this is considered as a base vector, and we need to find out the other vector which are orthogonal to this base vector. Okay. So we will do this orthonormality later. First, we do the orthogonal portion. Okay. Now we need to find out the vector B. So vector B is basically small b minus A transpose B by A transpose A into A, right? So what is B vector? So what is B vector? It's a 2, 0, -2, right? Minus A transpose. A transpose is 1, -1, 0, and then 2, 0, -2, whole divided by A transpose A. So we can do this division sign because here A transpose A is a scalar. If it's not a scalar, then we can't do this in a division format. We have to do it in a mat because it's not a scalar term, it's a matrix term. So we use inverse over there. And then A, 1, -1, 0. So what we get 2, 0, -2. And this one is 2, 0, 0. So 2 divided by this is. So this is 2 divided by this is 1, 1, 2, right? Yeah. And this is 1, -1, 0. So what we get? We get 1, 1, minus 2, right? So this is the capital B vector, which is orthogonal to A vector. So let's check like whether it's orthogonal to A vector or not. So what is the orthogonality definition? It's basically if the two vectors are different, then its dot product is 0, right? So A transpose V has to be 0. If it is not 0, then it's a not, I mean, I did something wrong. So it comes out as a 1 minus 1, and then it's a 0. So that means they are orthogonal. So orthogonality checking done. Okay, now I have to find out C vector. C vector, what is C vector? Definition: small c minus A transpose C by A transpose A into A. Yeah, into A minus, sorry, B transpose C by B transpose. This C, these C's are small c. These C's are small c's, not a capital C. Okay. C. So what is C vector? It's a 3 minus 3, 3. Okay. Now minus A transpose, which is 1 minus 1, 0, with the 3 minus 3, 3, divided by 1 minus 1, 0, 1 minus 1, 0, and here 1 minus 1, 0. And now I have to subtract V vector as well. So what is V vector? Capital V, not small v. It's a 1, 1 minus 2, because and then multiply with 3 minus 3, 3, division 1, 1 minus 2 with the 1, 1 minus 2, and here 1, 1 minus 2. Okay. So here 3 minus 3, 3. Okay. Now this is 1. This is 3 plus 3. This is 6. 6 divided by 2. Yes. 1 minus 1, 0. And this is 3 minus 3, 0, minus 6. And this is 1, 1, 2. 2 plus 4, 6. 1, 1 minus 2. Right? So what is the ultimate answer? 3 minus 3, 3, minus 3 minus 3, 0, plus 1, 1 minus 2. So the ultimate answer is 1. This is 1, and this is 1. Right? 1, 1, 1. Now check the orthogonality. What is? Let's see whether these are orthogonal to each other or not. So A transpose C, first have to check 1 minus 1, 0, and then 1, 1, 1. So I'll get 1 minus 1, this is 0. Check. And then next checking is B transpose C. So what is B? 1, 1 minus 2, and this is 1, 1, 1. So this is 1 plus 1 minus 2, this is 0. So that means A, capital B, and capital C all are orthogonal. Now we need to do it. We need to transfer this to an orthonormal. Like we need to divide all this vector by its length so that we get a unit length vector. So that means Q1 is basically A by norm of A. So norm, what is norm of A? Norm of A is basically A transpose A, right? So A transpose A is norm of A. So it is basically 2. So 1 minus 1 is basically half minus half 0. This is Q1. Q2 is B by norm of B. The norm of B is basically that B transpose B. So what is B transpose B? B transpose B is basically 6, right? This term B transpose B is basically 6. So it is 1 6, 1 6, and minus 1/3, and Q3 is basically Oh, sorry. I did a mistake. A transpose. I did a terrible mistake. Terrible mistake. Norm of A is basically, I have to write it over here. A by root under A transpose A. It's not A transpose A, it is root under A transpose A. So it should be 1 by root 2, 1 by root minus 1 by root 2, 0. So this should be 1 by root 6, 1 by root 6, and minus 2 by root 6. Okay, and then Q3, which is equals to C by norm of C. The norm is this is C. So root under C transpose C is basically root 3, right? So, so it's 1 by root 3, 1 by root 3, and 1 by root 3. So we get that vector. Okay. So I hope this Gram-Schmidt process is clear to everyone. Now moving to that, I will slightly discuss about isometries, and then we will go to that eigenvectors and diagonalization process. Okay, I will not go details into that isometries. Okay. So isometries are something like, sorry. So if we consider an inner product space, okay. So let's say either it's a matrix space. When you say of matrix space, it's not matrix space, it's a metric. Metric means like where in that space all the distance has been calculated. Okay, so if we consider a inner product space, inner product space or a metric space, whatever. So if there is any linear transformation from that space to that space, I mean from that same space to that same space, if there is a linear transformation called T, then it is called isometry. If so, let V is an inner product space. Inner product is basically also that we are called um, if A and B are the two vectors, then A transpose B is basically the inner product of that vector. So this is V is an inner product space, and T is a linear transformation. So since we are dealing with all linear algebra, so there is no nonlinearity. So T is a linear transformation from V to V. Okay, so it takes the values from V and it placed in V. Okay, so is a linear transformation. Then T is called isometry on that vector space V. If we call this is, let's say we have a two vector V and W, and we take an inner product. So we sign this term. This is called bracket. Okay, bracket, cat. Okay, so is simply equals to V and W. So if we took an inner product of this two vector, and if we took a inner product after transformation of that vectors, we will see that the values of these two vectors are same. So if this is same, that then it is called isometry. That means this map basically preserves the angles between the vectors. So the angle between this V and W and angle between TV and TW, these two are same. There is no changes in the angle, and also the length is basically never change. Okay, so that means it preserves angles between vectors and preserves length. Like if the length means if length of V is norm of V, as we have seen that we are length basically the norm of V, norm of that vector, then length of TV, which is norm of TV, right? This should be the length, but this is also equals to norm of V. So length doesn't change. So this kind of properties of this transformation, these are called spatial transformation. This type of properties is called this type of scenario. Sorry, this type of transformation is called isometry. Okay. So like here, a small example, if we consider. Okay. So T is a vector. Consider T. Sorry, T is a transformation that takes values from real number and map to the real number. Okay. And how this transformation going on? I mean, how this transformation looks like basically. So T of x is something like alpha x, where x belongs to this R. Okay. And alpha is basically fixed. Alpha is some any linear number. So to make this T, this transformation, so the question is basically to make this transformation an isometry. So what should be the value or what should be the value of alpha so that this transformation happen? I mean, this transformation become an isometric transformation. Okay, so did you understand my question? Like I'm saying, so this is the type of transformation. Like when we apply this linear transformation on vector, is basically multiplied with alpha. So what should be the value of alpha so that this transformation becomes an isometric transformation? Okay, so it is very easy. Like you can intuitively you can check. I mean, you can understand that. So what is the thing? What is the rules of isometry? So norm of T of x should be norm of x, right? So what is norm of T of x? It's basically alpha x that should be equals to norm of x. So by using the norm property, we know that because alpha over here is basically a scalar term. So we know that norm of x, we can pull out this alpha term and we do it in a absolute. We basically need an absolute value of that constant term. We do not need the signed value of the constant term. So, so from here we can see that if mod of alpha is basically 1, then T is isometry, right? So mod of alpha, so here the transformation should be only either 1 or minus 1. So alpha, the values of alpha should be either 1, or if alpha is a scalar over here, so values of alpha can be either 1 or minus 1. Okay. So if this is happen, then all this whole isometric property become isometric property preserve basically. It preserve the length, it preserve the angle, whatever. Now let's move to the more interesting topic, that is eigenvalues and eigenvectors. So from the first day we have seen that we have basically seen that when we multiply a vector with a matrix, we get another vector, right? We get another different vector. But sometimes we get the same vector with a scaled version of that vector. Either it's a enlarged version of that vector or a shrinked version of that vector or the similar vector, right? So those vectors are basically the spatial vectors. Those vectors are called eigenvectors. And the values of the scaling and that scaling part is basically known as the eigenvalue. Okay, so so suppose V is a vector. So if we multiply a matrix A with a V, we get a V, but we get a scaled version of V. Let's say some scaled by some lambda. Its lambda could be, I mean, it makes the vector enlarged version of the previous one, or it makes the vector the shrinked version of the previous one. So it could be anything. So this is called eigenvalue, and this vector is called eigenvectors. Okay. Now, this eigenvalues and eigenvector basically it it defines many characteristics about the matrix, about the multiplying matrix. Okay, just a minute. So we know, have you ever studied, how to find out the eigenvalue? How you, do you have any idea about how we can find out the eigenvalues and how we can find out the eigenvectors? Do you have any idea about anything like how we can find out eigenvalues and eigenvectors of a matrix?
By using determinants a minus lambda I.
Yeah, by this characteristics polynomial, using the characteristic polynomials, we can find out the eigenvalues of matrix, definitely. And then using that values, from here we can see that, so from this equation, what we can see is basically a minus lambda I into V is basically 0, right? So this is, let's say, another matrix, something. Let's say I call this matrix as a, let's say, A bar. So A bar B equals to 0. So we have studied, also there is another definition of this eigenvector. So we have studied null space, right? So this is basically nothing but a null space of this A bar matrix. What is the eigenvector? Eigenvector basically the null space of this A bar matrix, right? Because we studied that AX equals to 0. The solution of that AX equals to 0 is basically the null space, the basis of the null space. So uh, the first definition that we have studied and that we have studied over here with the eigenvector are the spatial vectors. If we multiply this vector with a matrix, then we get the scaled version of this matrix. Okay, either the same scaled version of this vector, either the same vector or the shrink or enlarged vector. Or another definition you can consider this, like eigenvector is basically the null space of A minus lambda I. Is basically the basis of the null space of A minus lambda I, right? So we need to find out the null space solution of A bar. So try to find, try to start with a small example. Okay, 2 cross 2 example. So here the matrix is 0.8, 0.3, 0.2, and 0.7. So this matrix is also a very special matrix. If you see that columns, all columns are, if you added the elements of columns, you will get value 1. So this matrix is called Markov matrix. Okay. If a matrix, all the columns, if you add all the columns and you will get 1, add all the elements of the columns and you if you get the value 1, then those matrix called Markov matrix. So we need to find eigenvalues and eigenvectors. Okay. So eigenvalues is basically determinant of A minus lambda I. And we need to find out the roots of the characteristic polynomial. Okay. So this is 0.8 minus lambda, 0.3, 0.2, and 0.7 minus lambda. Okay. So it's a 0.8 minus lambda, 0.7 minus lambda, minus 0.06, right? Yeah. So it's 0.56. This is 1.5 lambda plus lambda square minus 0.06. So what we get, lambda square minus 1.5 lambda plus 0.5, right? So what we get is basically lambda square 1.5 lambda minus 0.5 lambda. Yeah. So this is something lambda minus 1 and lambda minus 0.5, right? So what are the eigenvalues? It's a lambda 1 equals to 1 and lambda 2 equals to 0.5. Okay. So now we need to find out the eigenvector. That means we need to find out the null space solution of A minus lambda I. So first we use the lambda 1. Now using lambda 1 equals to 1. So what I need to find out is A minus lambda 1 I V1 is equals to 0. Okay. Now I need to put lambda 1 over here, right? 0.8 minus 1 is minus 0.2, 0.3, 0.2, minus 0.3. It's a V11 and V21. And this is 0, 0, 0. So either you can do that Gauss elimination method and find out this value, or this is very simple. The value are basically it's 0.2 V11 0 0. So it's basically from here we can see what are the values could be. We need to find out the value. This is V11 plus 0.3 V21 should be equals to 0, right? So here we need to value. So if we put value V11 is 1, so 0.3 is a 0.3 by 0.2 is 1.5. So this is V equals to, if we put the value of V211, so this would be 1.5, right? I think I'm right. Yeah. So this is one eigenvector. This is V1. So it could be a 3 by 2, or let's say if we put 0.6, yeah, either this, or you can consider V1 is a 0.611 and V21 is a 0.4. This is also an eigenvector. Okay. So now using lambda 2 equals to 0.5, right? So it's a minus lambda 2 I V2 equals to 0. Okay. So now lambda 2 I is 0.8 minus 0.5. This is 0.3, 0.3, 0.2, and this is 0.2, right? This is 1, 2. This is 2, 1, V2, 2. This is 0, 0. So this is very easy. V2 could be consider 1 minus 1, or you can consider V2 as minus 1, 1. Either any of them are the eigenvector, right? So that means if we multiply A with the V1, we should get V1. And if we multiply A with V2, we should get half V2, right? So let's check whether it is happening or not. So first point 1.51. So what I will get, it's 0.8 into 1.5 plus 0.3. So I will get 0.8 into 1.5. It's 3 by 2, 8 by, it's 8 by 10 into 3 by 2. So 12, 1.2, 1.2 plus 0.3 is 1.5. And here 3 by 2, 0.3 plus 0.7 is 1. And if we do the same thing with the 1.2, 0.3, 0.7 with the 0.6, 0.4, so what we get, it's a 0.48 plus 0.12. 0.48 plus 0.12. What is 0.48 plus 0.12? It's am I doing something wrong? Let's check. 0.8 into 0.6. Yeah. Plus 0.3 into 0.4. Yeah. Oh, sorry. Yeah. 0.48 plus 0.12 is basically 0.6. Yeah. That's true. And 0.12 plus 0.28 is basically 0.4, right? So that means V1, that means this is the eigenvector. And if we do the same thing over here, 0.8, 0.5, sorry, 0.3, 0.2, and 0.7, multiply with 1 minus 1, what we get? 0.8 minus 0.3 is 0.5, and 0.2 minus 0.5 is minus 0.5, which is 0.5 or half multiplied with vector this, right? The similar case, this case, we will get the similar result. Okay. So this is basically the eigenvectors and eigenvalues. So any doubt over here? If you have any doubt, you can please ask, or I'll move to the next one. Okay. So eigenvalues could be imaginary. It's not necessary that eigenvalues are always be real. Okay, it could be imaginary. If we use uh, what we called a reflection matrix, then its eigenvalues, yeah, then its eigenvalues are eigenvalues comes out as a imaginary, like reflection matrix in the sense like identity matrix, but the diagonal elements are not in that form. It's basically off diagonally. I mean, we know that in identity matrix, so we know that identity matrix is 1 1 something like, or 2 cos 2. But here I'm saying that in that case, so the eigenvalues imaginary comes out as imaginary. So it's not necessary that eigenvalues can be an real eigenvalues. So if eigenvalues are not real, if eigenvalues are not real, then it's possible that eigenvectors are complex in nature, right? So, but if the matrix is symmetric matrix, I will get into that topic later. But if the matrix is symmetric matrix, then its eigenvalues always be a real. Okay, that is for sure. Now, I hope there is no necessity to do this whole eigenvalues and eigenvectors things for 3 cross 3 matrices. Okay. So now move to the diagonalizing. So let me ask you, I mean, is it clear with this one example how this eigenvalue and eigenvectors you can find out? Is it clear to you?
Yes, sir. Clear.
Yeah. So I'll move to the diagonalizing of a matrix. So diagonalizing is basically like we can represent a matrix with with its diagonal form. Diagonal form means where all the eigenvalues are in the diagonal lies in diagonally. Like it's something like a identity matrix, but all the off diagonal elements are zero, and all the diagonal elements are the eigenvalues of that matrix. So it could be possible. So first of all, if the matrix has uh, distinct eigenvalues. First of all, if the matrix has distinct eigenvalues means let's say in this case, in this particular example, you see that the eigenvalues are distinct in nature, right? But sometimes it's possible that eigenvalues are not distinct. We get the similar eigenvalues, like lambda 1, lambda 2. If it is something like, if we get that lambda minus 1 whole square equals to 0, right? So we will get that eigenvalues are similar. Okay. So lambda minus 1, lambda minus 1. So we get a same eigenvalue. First case, if a matrix have distinct, if a square matrix, definitely, if a square matrix have a distinct eigenvalues, then we can diagonalize those matrices properly. So does that mean that if matrix has similar eigenvalues, we cannot diagonalize it? No, it's not true always. We can diagonalize those matrices. For that case, we need to know the, like, what do you call it? The number of the eigenvectors are dependent or independent. Okay. So if the eigenvectors are dependent, then we cannot find the diagonalizing, we cannot diagonalize that those matrices. But for similar eigenvalue, we have independent eigenvectors, then we can find out the, we can diagonalize those matrices. So we cannot diagonalize it properly, but we can find out the similar matrices. Okay. So let me just a moment before comes to this topic. Yeah. So here we call two things we need to remember. So for case for the distinct eigenvalue, we know that algebraic multiplicity. There are two terms that you need to know. The first thing is algebraic multiplicity and geometric multiplicity. So algebraic multiplicity means, so here in this case, in this matrix, we have a two eigenvalues. Two eigenvalues are distinct. So that means the algebraic multiplicity of lambda 1 is 1 and algebraic multiplicity of lambda 2 is 2, because we did not find lambda 1 twice, right? We get the value 1, we get value 1 once, and we get value 0.5 once. So that means the algebraic multiplicity is 1 and geometry and algebraic multiplicity of lambda 2 is 1. And geometric multiplicity means using these eigenvalues, we get an one distinct eigenvector, either this or this. That doesn't matter, but we get one distinct eigenvector using this eigenvalue. Using this eigenvalue. Okay. So that means the geometric multiplicity is also 1 for that case. And here the geometric multiplicity also 1 for this case. Okay. Now, if algebraic multiplicity equals to geometric multiplicity, then we can say that we can diagonalize those matrices. But for similar eigenvalue case, it sometimes happens that for similar eigenvalues means for 2 cross 2 matrix, we get two eigenvalues, right? Lambda 1 and lambda 2. But both are similar, like lambda 1 equals to lambda 2, let's say is equals to 1. So that means the algebraic multiplicity of lambda is 2 now, right? Because we get 1 twice. We get this eigenvalue twice. So that means algebraic multiplicity of that eigenvalue is 2 now. So in that case, if the geometric multiplicity of that eigenvalue is also 2, then we can diagonalize it. If it is not possible, if we cannot find another eigenvector using the same eigenvalue, then we cannot diagonalize those matrices. So this is basically the overview of diagonalizing of a matrix. First, we will check how to do the diagonalization process, and then we go to the algebraic multiplicity and geometric multiplicity. Okay. So, so why is it something like that? So suppose A is a matrix and we need to diagonalize it. So let's say I call it a big lambda equals to S inverse A S. So this is the formula of diagonalization. So what is S and S inverse? So S is basically its column is basically filled with the eigenvectors. Okay. So that means let's say V1, V2 up to Vn. So its column is basically filled with the eigenvectors. Okay. So now we have seen already in previous discussion. So if the matrix have distinct, if the matrix have independent column, then the rank of this matrix is full. So obviously I'm talking about the square matrix here. Now, from now, I'm not talking about any kind of rectangular matrix because we cannot find out inverse determinant of any rectangular matrix. Okay. So we have studied that if the columns of the matrices of this of a matrix is are independent, like they are not dependent on any other, then the rank of this matrix is full rank matrix, and we can find out the inverse of this matrix. So from this definition, so from here in the definition of diagonalization, so we can see that inverse is basically used over here, right? S inverse S, S inverse A is. So if the matrix, the columns are dependent, we cannot find out the inverse because matrix is not full rank. So if matrix is not full rank, so that means its determinant is zero, right? And in to find out the inverse, we need a determinant. So that's why we cannot find out the we cannot diagonalize those matrices whose eigenvalues are dependent on each other. Okay, that's why for distinct eigenvalues, we will definitely find distinct eigenvectors. There is a no possibility of getting the there is a no possibility of getting this dependent eigenvector for distinct eigenvalue. But for similar eigenvalues, sometimes is a possibility that we get dependent eigenvectors. So that's why this is the one process. And also sometimes if we multiply with s on both sides, from here what we get is basically as. Now a is equals to s lambda s inverse. So why is diagonalization is required? Because sometimes in calculation, in doing some work, so when we need to, when we are basically doing work with the matrix, so it is very easy to deal with a diagonal matrix than a matrix than a proper matrix. Okay, since these matrices are basically similar, the nature and properties of these matrices, this big lambda and a, these two matrices, the big lambda and a, these two, the nature of these two matrices are basically similar. So that's why it is preferable to work with the easy matrix than the difficult one. So that's why we need a diagonalization kind of thing. Okay. So we know that so this lambda This lambda is basically nothing but lambda 1, lambda 2, let's say up to lambda n, right? So if someone says the eigenvalue of A matrix, let's say A is a 2 cross 2 matrix. Now eigenvalue of A matrix you need to find out. Eigenvalue of A matrix you know, or you can find out by using all this procedure for 2 cross 2 matrix. Now someone says that find out the eigenvalues of A to the power 100. It would be difficult using that same process, right? You multiply A 100 times and then do all those processes. So it will be difficult, but here you can do one thing. So since A is equals to S lambda S inverse, so what is doing S square is basically A S inverse multiplied with S lambda S inverse, and you have to do S lambda S inverse S lambda S inverse. This term is basically nothing but I. So what we'll get is lambda square S inverse. So that means lambda become lambda square, lambda cube. Similarly, a to the power k equals to a lambda to the power k S inverse. And you can find out the eigenvalues for that case. Now I have a question, I have a problem regarding this. So do you know what is Fibonacci series, Fibonacci number?
Yes, sir.
You have an idea, right? So we have a sequence something like that, and and the question asks that you need to find out the 100th number. Okay. So if you have a Fibonacci sequence, the sequence is basically something like 0, 1, 1, 2, 3, something like 5, 8, 13, something like that. And now you are asked that you have to find out the 100th number of this Fibonacci sequence. So you can do it 100 times and then find out the value of the 100th number, or you can use the linear algebra. Okay. So the question is, find the Fibonacci number F100. Okay. So we know that this F k plus 2, because these two term are given to you. We know the first term and the second term, and then we can continue this process. Okay. So Fk plus 1 is basically what is Fk plus 2 is basically Fk plus 1 plus Fk, right? So put F2, so F2 is basically F1 plus F0, F3 is basically F2 plus F1. So this is the one equation that we get. And another equation is something like Fk plus 1 is equals to Fk plus 1. So that means, so this is Fk plus 2, this is Fk plus 1, right? And then we can write it in a matrix vector format. This is 1, this is 1, this is 1, this is 0. Sorry, this is 1 and this is 0. Fk plus 1 and Fk, right? So this is now your A matrix. Okay. You need to find out the 100th number. So let's say we call this as a UK. So UK is basically your Fk plus 2, Fk plus 1, right? So that means it means that U0 is basically F2 and F1. U1 is basically your F3 and F2, right? So similarly, U100 is basically your F101 and F100, right? So F2 and F1 is basically 10, and this is 11 because we know that series. Okay, F100. So first of all, we need to find out the eigenvalues of A matrix. What is the A matrix? I write it down over here again. Okay, I need to find out the determinant of A minus lambda I equals to 0. So I need to find out 1 minus lambda, 1, 1 minus lambda. This is 0. This is lambda into lambda minus 1 minus 1. This is lambda square minus lambda minus 1. So what is lambda equals to 1 plus minus root under 1 minus plus 4 divided by 2. 1 plus minus root 5 by 2, right? 1 plus minus root 5 by 2. So this is something like 1 plus root 5 by 2, something 1.618, and then minus 0.618. These are the two values. Okay. Now you need to find out the eigenvector of those using this whole process. So using lambda 1 equals to 1.618, we need to find out the eigenvalue, right? Estimate. So it's basically minus 0.618, 1, 1 minus 1.618. So 0.618 into 1.618. So what is this? So this one is basically, this is basically 1 plus root 5 by 2, and this is basically 1 minus root 5 by 2, right? So if we do one thing, what we get, so this is nothing but 1 minus, so this term is nothing but 1 minus half minus root 5 by 2, right? So this is basically 1 minus root 5 by 2. So this term is 1 minus root 5 by 2. And what is this term? This term is minus 1 plus root 5 by 2. So if you multiply these two things, 1 minus root 5, 1 plus root 5, what we get? Minus 4. So if we do the 1 minus 5 4 1 minus 5 by 2 0 0. Sorry, yeah. So this is, yeah. So yeah. Sorry for that delay. So if we multiply this term, so if we multiply this term with this term, we will get definitely we will get -1, right? So that's why if we choose v21 equals to 1 and v12 equals to 1 and v11 equals to 1 plus root 5 by 2 or lambda 1, right? We will get this answer. So v1 equals to something like that. Now using lambda 2 equals to 0.618. So if 0.618 or something like 1 plus root 5 by 2, this is 1 minus root 5 by 2. So something 0.618. So it become 1 minus of plus root 5 by 2. So 1 plus this would become 1 plus yeah 1 plus this is become 1 plus root 5 by 2. This is 1, this is 1, this is minus 1 minus root 5 by 2. And this is v21, this is v22, this is 0 0. A similar process. So if we choose v22 equals to 1, so v21 is become 1 plus minus root 5 by 2, then that is lambda 2. So my v2 equals to basically lambda 2 1. Okay. Now we get this v1 is equals to lambda 1 1 and v2 equals to lambda 2 1. We need to find out something like u100. What is this equation? This is hmm, sorry. I did a big mistake over here. This is uk plus 1. This is uk. So this should be something k plus 1 k. Okay. u0 is f0, f1. u1 is f2, f1, and this thing. Sorry for this mistake. So this is UK, this is UK plus 1. Okay, so UK is basically FK plus 1, FK. So when u naught is basically f1 f0, because we have only f0 and f1 term, and from here we find out that f100 terms, right? So that means u100. So we know that uk plus 1 equals to a uk, right? So we need to find out, that means u naught equals to, sorry, u1 equals to u naught. Now u2 equals to a u1. So a u1 means a square u naught, because you are only given the initial values, right? You are not given, and from here you're finding out that all the subsequent values. So similarly, u3 equals to a cube u naught. So similarly, u100 equals to a100 u naught. So a100 multiplied with u naught. So how do you find this a100? We have this thing, a100 equals to s lambda s lambda to the power 100 s inverse, right? So what is s? S is basically lambda 1 1, lambda 2 1, and what is this? This is basically lambda 1 to the power 100, lambda 2 to the power 100, and this is S inverse. So how to find out this S inverse? S inverse would be, what is the S inverse? It's 1 lambda 1. This is minus lambda 2 minus 1, and divided by lambda 1 minus lambda 2, right? Something like 1 by lambda 1 minus lambda 2, 1 minus lambda 2. This is minus 1. This is lambda 1. So if you do these things, you will find out this a100, and you know the value of lambda 1, lambda 2. All those values is known to you, and you know the value of u naught. What is u naught? U naught is given to you, that is f1 and f naught. So from f1 and f naught, it is 1 and 0. You just multiply this with 1 0. So u100 will get. So what is u100? It is f101 and f100. So that the last element is basically you need to find out, right? So I'm not going to the details of this calculation. You can do it by your own. I mean, obviously to the power 100 finding out is very difficult, but you can, I mean, just consider as a to the power 100. You do not need to calculate it properly in that format. Okay. So this is just an example, like using this diagonalization process, uh, you can find the eigenvalues, or you can find the eigenvalues of the same matrix of any to the power, like the power could be anything. You can find it out very easily. Okay. So the next things that comes into the picture is algebraic multiplicity and geometric multiplicity. So as I have already discussed that algebraic multiplicity and geometry, what is algebraic multiplicity and what is geometric multiplicity, I'm again discussing this to make things clear. Algebraic multiplicity is basically the repetition of eigenvalues. Okay, is basically simply that repetition of eigenvalue of A. So how many repetitive eigenvalues do we get? It basically defines the algebraic multiplicity of that particular eigenvalue. Okay, and the geometric multiplicity is basically number of independent eigenvectors corresponding to that eigenvalue. Okay. So if for case of a similar eigenvalue, if we get, if we let's say the eigenvalues that for, let's say for 3 cross 3 matrix, you will get you basically about to get 3 eigenvalues, right, for 3 cross 3 matrix. So definitely these 3 eigenvalues are similar, like 3 eigenvalues is 1, let's say. Okay. So that means the algebraic multiplicity of eigenvalue lambda is basically eigenvalues of matrix A is basically 3, right? So in that case, if the geometric multiplicity is also 3, if the we need to find out that how many independent eigenvector we can find out using that yeah, what do you call using that eigenvalue, how many independent eigenvector do we get using that similar eigenvalues lambda. So using that eigenvalue 1, if we get 2 independent eigenvectors, that means we cannot find out the that means the geometric multiplicity of that eigenvalue is 2. That means uh, we do not have 3 independent eigenvector corresponding to similar eigenvalues. That means we cannot diagonalize this vector. I diagonalize this matrix. Okay. There is a one concept how to find out. Just a minute. So there is a one concept is called generalized eigenvalues and generalized eigenvectors. Okay. So what is generalized eigenvector? So I will just do one thing. Okay. So generalized eigenvectors. So what is basically the mean? What it basically means is this is only because if we have a distinct eigenvalue, we can find out the distinct eigenvector. But if we have a similar eigenvalue, we get one eigenvector using that lambda. But next time we need to find out the generalized eigenvector. Okay. Or before that, if we just a minute. Okay. Actually, I have no idea the whether you have I have whether you have studied in the video is professor covered this generalized eigenvector or not. I'm just let me check. If it is not, then it is not required. Just hold for a second. Okay. Just let me check whether professor has mentioned anything or not. No. Mm, No, so professor has not covered this concept of generalized eigenvector in this particular week. So I will not cover this week. I'll cover it on the next week as well. So till now, do you have any issues with understanding any topic? If you have, please ask me anything, any questions. If you do not have anything, then I will wrap it up. Okay. So kindly please let me know, like, do you have any query regarding today's discussion?
No, sir. From my side, no, sir.
From your side, it's okay. I mean, okay, then I think the another one is on hold from for a long time. So I don't know whether what's the problem with her. So yeah, so I'm just wrap it up over here. Then we will meet again next Saturday. And next Saturday and Sunday, consecutive 2 days, I have a class. I think you have that. I mean, notification also. You will get that notification that 8th March and 9th March, both 2 days. I will complete this 8 weeks course. Okay, so we will meet next week. Thank you.
Thank you, sir. Welcome.
Thank you.